Hello, Assalamu alaikum students. So let's solve some relevant numerical problems from the topic of buoyancy. So problem number 1 is find the volume of water displaced and the position of center of buoyancy for a wooden block of width 2.5 meter and depth 1.5 meter when it floats horizontally in water. The density of wooden block is 650 kg per meter cube and its length is 6 meter. So we can draw this figure which gives the width of this block 2.5 meter and its total depth 1.5 meter, and the perpendicular dimensions which give us the length, it is 6 meter. As it is given, it floats horizontally in water, so it is partially submerged, and here we have the water surface, and the depth of this object which is inside the water, the h, it is unknown. And if we can find out this h, we can get the volume of water displaced by multiplying it by the width and the length. And we also need this position of center of buoyancy. So the first step is to calculate the weight of the block. As we know, weight is specific weight into volume, and the density of this wood is given. So specific weight is density into gravitational acceleration. So 650 into 9.81 into the volume, which is 2.5 into 1.5 into 6. Multiplying that with gamma, we'll get the weight of the block. For equilibrium, the weight of water displaced is equal to weight of wooden block. So we have got this from the relationship. As we know, the force of buoyancy should be equal to the weight of wooden block for equilibrium, and the force of buoyancy, it is specific weight into the volume displaced. So we can rearrange this expression. For this volume displaced, we will get, it is weight of the wooden block divided by the specific weight of water. So from here you will get the volume displaced, and for the position of center of buoyancy, um, you can equate it to the volume displaced, trying to find out this h. And as we know, the center of buoyancy, it is at the center of the volume displaced, so it will be at 0.975 divided by 2, which is 0.4875 meters from base. So let's see the second numerical problem. A stone weighs 392.4 Newton in air and 196.2 Newton in water. So compute the volume of stone and its specific gravity. So if we have a stone which weighs 5 kg in air and 3 kg in water, so basically we can say that 2 kg of force of buoyancy is acting on that. So we're going to make use of this, and we're going to write that the weight of stone in air minus the weight of stone in water, this is equal to force of buoyancy, which is weight of volume of liquid displaced. So weight of stone in air is given, it is 392.4 minus the weight of stone in water, which is 196.2. So this is equal to 196.2, and the weight of volume of liquid displaced is basically the specific weight of water into volume displaced. So specific weight of water is 1000 into 9.81, and you can rearrange this expression and get this volume of water displaced, which is basically the weight of the stone. Now in order to find out specific gravity of stone, there are two ways. You can find out the specific gravity by taking the ratio of the density of stone to the density of water, or you can take the ratio of specific weight of stone to specific weight of water. So here they have given, they have used the density ratio. So the weight was given, weight in air, it is 392.4, and we can get the mass by dividing it by 9.81, and the density of stone will be the mass in air divided by the volume, which is 2000 kg per meter cube. And from here you can get the specific gravity of stone. Problem number 3 is find the density of metallic body which floats at the interface of mercury of specific gravity 13.6 and water such that the 40% of its volume is submerged in mercury and 60% in water. So if we have the total volume of V meter cube of the body, so 0.4 V is submerged in mercury and 0.6 V is in water. And the total buoyant force, it could be computed as force of buoyancy due to water plus the force of buoyancy due to mercury. So force of buoyancy due to water will be the weight of water displaced by the body. So density of water into gravitational acceleration into volume of water displaced. So 1000 into G into 0.6 V. And the force of buoyancy due to mercury, it will be the density of mercury, which is 13,600 into gravitational acceleration into volume of body mercury, which is 0.4 V. So for equilibrium, we know this total buoyant force, which is summation of buoyant force in mercury and in water. This should be equal to the weight of the body, which is specific weight into G into V. The G and V, it will cancel out, and we will be left with this unknown density only, and we can rearrange this expression and get this rho in kg per meter cube. So the fourth numerical is a rectangular pontoon has a width B of 6 meter and a length L of 12 meter and a draft D of 1.5 meter in fresh water having density 1000 kg per meter cube. So let me explain the draft with the help of this figure. And as you can see, the part of that object which is submerged in water is called draft, and the above part is called freeboard. So a rectangular pontoon, you can say it is a wooden plank having width 6 meter and a length 12 meter, and its thickness or the depth is submerged, and as it is floating, so the part of that pontoon which is inside the water, its thickness is 1.5 meter, which is called draft. Now calculate the weight of the pontoon. The second part is its draft in seawater having density 1025 kg per meter cube, and the load in kilonewton that can be supported by the pontoon in fresh water if the maximum draft permissible is 2 meter. So as we know, the force of buoyancy, that is the upthrift force, it should be equal to the weight of the pontoon for equilibrium, and we can calculate the weight of the pontoon using this relationship, which is equal to force of buoyancy, which is weight of fluid displaced, and we can calculate that weight using specific weight into volume. Specific weight is density into gravitational acceleration, and volume is BLD, the volume displaced. We have already been provided with the draft, so it will be width into length into depth. Simply replacing all the values, you will get this weight of the pontoon 1059.5 kilonewton. Now the second part was when the density of the seawater is 1025 kg per meter cube. So calculate the draft in seawater. So rearranging that expression for the draft and using the same weight as calculated 1059.5 and converting it to newtons, because we're using the density in kg per meter cube and acceleration in meter per second square, so the values should be in meters, 1.46 meters. So they've asked us the additional load that can be supported if the draft permissible has been increased to 2.5 meter in fresh water. So the density will be 1000 and the draft here is 2 meter. So the total upthrow force, now this will be 1412.6 kilonewton, and the additional load would be subtracting the weight of the pontoon, and that is we'll get 353.1 kilonewton. So problem number 5 is a cylinder 1.8 meter in dia, 1.2 meter high and weighing 10 kilonewton floats in salt water of density 1025 kg per meter cube. Its center of gravity is 0.45 meter from the bottom. If a load of 2 kilonewton is placed on the top, find the maximum height of the center of gravity of this load above the bottom if the buoyant is to remain in stable position. So this cylinder, which is 1.8 meter in dia and 1.2 meter high, it weighs 10 kilonewton, and it is given G is the center of gravity of this 10 kilonewton cylinder, which is at a distance of 0.45 meter from the bottom, and additional load of 2 kilonewton is applied, and its center of gravity is G1 and the distance from the bottom is Z1. And as we know, additional weight has been applied, so for the complete body of 10 plus 2 kilonewton, that is 12 kilonewton, so its center of gravity will be shifted, and the new position of center of gravity, it is G dash, and its distance from the bottom is Z dash. So the first step is to calculate the buoyant force, which is equal to weight or volume of liquid displaced, and we can get that using this rho GV, where volume would be area of that cylinder, which is pi by 4 d square, into the draft, that is a submerged part of the object. So this draft Z is because of the complete weight W plus W1. This W is 10 kilonewton and W1 is 2 kilonewton. So this buoyant force, it has to be equal to the weight of the object for equilibrium, and in this equation the only unknown is Z, so rearrange it and substitute all the values and you'll get 0.47 meters. So the center of buoyancy, it will be at the center of gravity of the volume of liquid displaced. So this distance B, it will be at half Z from the bottom. So the distance OB is equal to half Z, which is 0.235 meters. Now for this object and the load to be in equilibrium, the metacenter must be coinciding with the center of gravity G dash. So in that case, the metacentric height G dash M will be 0 and the metacentric radius BM will be equal to BG dash. And as we know, metacentric radius is moment of inertia over volume displaced. So it is pi d 4 over 64 divided by pi d square over 4 into Z. So replacing all the values, you'll get BG dash equal to 0.431 meters. So let's locate this G dash point, which is at a distance of Z dash. So this Z dash will be simply OB plus BG dash. So 0.235 plus 0.431, which is 0.66 meters. So after that, the only thing unknown is this Z1. So let's take the moment about this O point, and it will be the W1, which is just 2 kilonewton weight, into the distance of G1 till point O, which is Z1. So W1 into Z1 plus this W weight, 10 kilonewton, into its the distance from its center of gravity till O point. So this G, it is located at 0.45 meters. So plus 0.45 W is equal to the total weight and their combined center of gravity, which is G dash, the distance from this G dash till point O, which is Z dash. So W1 till its distance Z1 plus this weight 10 kilonewton, and the distance from its center of gravity, which is 0.45. This is equal to the combined weight and the combined center of gravity, its distance is Z dash. So simply rearrange it and substitute all the values, and you'll get Z1 0.746 meters. So the last numerical problem is a solid cylinder of diameter 4 meter has a height 4 meter. Find the metacentric height of the cylinder if the specific gravity of the material of cylinder is 0.6 and it is floating in water with its axis vertical. State whether the equilibrium is stable or unstable. So let's see the figure first. We have the cylinder. This is the front view. It is floating in water. So this is the water level, and its total height is 4 meter. And this is the top view or the plan. It has a diameter of 4 meter. So we can get the depth of cylinder in water, that is this draft, and this will be equal to specific gravity into the height, that is 0.6 into 4, which is 2.4 meter. So we have got this using the basic equilibrium equation. As we know, for equilibrium, this force of buoyancy, it should be equal to weight of that object, and force of buoyancy is weight of volume of liquid displaced. So it is specific weight of the liquid into volume displaced, and the weight of the object is specific weight of the block into volume of block. So rearrange it for volume displaced. We'll get this ratio of specific weight of the block to specific weight of water, which is basically the specific gravity. And we know for the volume displaced, it will be area into the draft, and for the block, it will be area into the total height. So this draft D is specific gravity into H, the total height. So it was given that the specific gravity of material of cylinder is 0.6. So 0.6 into total height 4, we will get this draft, which is 2.4 meter. And the center of buoyancy, B from A, this distance will be the centroid of the submerged part of the object. So it will be 2.4 divided by 2. So it is AB is 1.2 meters. So the distance of center of gravity of the cylinder from A point, this will be at the center of this total height. So it is 4 divided by 2, so 2 meter, and we can get the BG, which is AG minus AB, so 2 minus 1.2, which is 0.8 meter. So now in order to calculate the metacentric height GM, we are going to assume that metacenter lies above the center of gravity, and this distance GM, this is equal to BM minus BG. So BM, which is metacentric radius, this is a ratio of moment of inertia about longitudinal axis to volume displaced, I over V, and we know moment of inertia for cylinder, it is pi d4 over 64, where diameter is 4, and volume of liquid displaced, this will be area into the depth of cylinder in water. So pi by 4 into d square, which is 4 square into 2.4, and this came out to be 0.4167 meters. So replacing the values in this equation, and 0.4167 minus 0.8, so it is minus 0.383 meters. So this means that our assumption was incorrect, that is metacenter lies below the center of gravity, so it will be an unstable state of equilibrium. So that's it. Thank you very much. Allah Hafiz.